Every interaction you have with physical reality is currently understood through a strictly localized sensory motor loop. The biological brain receives data through physical sensors, processes it, and generates a physical response. It is mechanically bound by what it can touch, see, or directly infer. This schematic outlines the standard model of modern neuroscience. Cognition operates strictly within these parameters. Information cannot enter the system from the future, and it cannot arrive from a spatial location outside the immediate reach of the sensory organs. Parapsychology asks whether biological systems ever bypass these strict physical channels. It tests whether the brain can occasionally access or influence information in a way that violates local space and linear time. In cognitive science terms, this is framed as the study of extended information processing. It treats the mind not as a closed, localized loop, but as a system capable of pulling data from non-local and non-temporal channels. This inquiry operates independently of the cultural mysticism often associated with the field. Researchers are testing a precise biological hypothesis: the existence of sensory pathways that do not rely on standard physical mediation. Removing spatial and temporal restrictions completely redefines the mechanical limits of the human mind. The task for researchers is proving that these extended pathways actually generate measurable data. Testing anomalous cognition demands strict scientific enforcement. Laboratories investigating these boundary-defying effects use the exact same empirical tools as mainstream psychology: double-blind trials, statistical controls, and high-fidelity physiological measurement. The research produced in these labs is typically partitioned into two primary categories of data: qualitative and quantitative. Qualitative data captures subjective internal states. In a free response trial, a subject describes unconstrained impressions or images, which independent judges later evaluate for recurring patterns or direct correspondences with an isolated target. When we shift our focus to the right side, we see the mathematical baseline used in quantitative trials. In a forced choice paradigm, participants select from a strictly limited set of options. Because the probabilities are mathematically fixed, researchers can map exact statistical deviations over thousands of trials. The objective is capturing subtle, statistically significant deviations from chance expectation within highly controlled environments. The first parametric extension researchers test is precognition, removing the linear temporal bound from the cognitive input loop to see if the brain can acquire information about the future. Notice the contrast in this diagram. The top represents standard predictive processing, where the brain uses past data to guess the future. The bottom models precognition as a temporal extension, a vector where an unpredictable future event sends data backward to the present brain. In present-tense studies, subjects are connected to physiological sensors while a computer randomly prepares an emotional or neutral image. This animated graph plots the response. The nervous system spikes a full second before the algorithmic marker selects the stimulus. The biological reaction precedes the event. This retroactive effect is also tested through associative remote viewing, or ARV. Participants record free response impressions today, which are strictly judged against a future binary outcome, such as the closing price movement of a stock tomorrow. Experimental psychologist Daryl Bem isolated this further by reversing standard psychological memory paradigms in time. Subjects consistently performed better on recall tests for words they would only be given to study after the test was already complete. When autonomic baselines and recall accuracy react to unselected future variables, biological intuition acts as a nonlinear temporal sensor. The second parametric extension tests spatial limits, determining if biological networks can acquire information across physical distance without any conventional transmission hardware. In the laboratory, telepathy is defined mathematically as inter-brain information coupling. It tests whether two isolated neural networks can achieve spontaneous synchronization. In the Ganzfeld protocol, a receiver is isolated in an opaque sphere. A distant sender attempts transmitting a target image via an inter-brain vector. Removing the sender tests clairvoyance, checking if the isolated receiver establishes a direct data vector to a hidden physical target. Similar non-local tracking occurs in remote staring experiments. Subjects are placed in isolated rooms, and their autonomic physiological shifts are recorded precisely when attention is directed at them through a closed-circuit camera from a separate building. Isolating subjects physically while proving they still exchange data challenges the premise that human nervous systems operate as entirely closed local networks. Shifting from cognitive input to motor output brings us to psychokinesis, or PK. This tests the hypothesis that consciousness can operate as a direct output force, influencing matter without physical contact. While historical reports focus on macro-PK, observable physical anomalies like moving objects, modern empirical research relies exclusively on the highly controlled statistical domain of micro-PK. This chart maps a perfect Gaussian distribution from a random number generator. In a micro-PK trial, participants attempt to consciously bias the outputs. A mathematical anomaly occurs when the subject's concentrated intention pushes the curve's statistical mean measurably away from chance expectation. Researchers rigorously track experimental modifiers. In psi-missing trials, subjects consistently score far below chance probabilities. Statistically, this is interpreted as a directional subconscious avoidance effect rather than random error. Performance is also heavily modified by the sheep-goat effect. Participants who score high on psychological metrics for prior belief in psi phenomena, the sheep, produce statistically different deviation rates than skeptics, the goats. Treating human intention as an independent physical variable blurs the assumed boundary between an observer and the environment they inhabit. The logical extreme of the extended cognition model is testing whether consciousness can sustain itself independent of a localized biological node entirely. Out-of-body and near-death experiences present high-stakes testing environments. Researchers attempt to place remote physical targets in operating rooms, checking if patients in states of total physiological shutdown can accurately report visual data upon resuscitation. The same strict blinding protocols used in associative remote viewing are applied to post-mortem survival hypotheses. Here, researchers test the factual accuracy of information provided during mediumship readings, controlling for generalized statements and cold reading techniques. In neural entanglement paradigms, simultaneous EEG and fMRI recordings look for spontaneous, synchronized brain activity between two spatially separated individuals, mapping correlations that exceed the expected baseline of random coincidence. These extreme parameters serve as the ultimate stress tests for the standard sensory motor loop, searching for the exact breaking point of localized processing. This network map represents the fully realized framework. Parapsychology translates concepts of non-local awareness and future prediction into highly mathematical, testable hypotheses about information boundaries. While mainstream science maintains deep skepticism regarding these conclusions, the physiological arrays and statistical baseline tools deployed to gather the data are undeniably rigorous. Anomaly hunting is a structural necessity for scientific advancement. Documenting persistent deviations from expected norms is exactly how rigid paradigms are eventually forced to expand.